Hi everyone. In this video, we're looking at the only section we talk about from Chapter 8, which is Section 8.1. So in Chapter 8, we're talking about sampling distributions. So instead of just looking at individual little X values or individual data points, what we're going to be doing is we're looking at, from a whole population, we're looking at a bunch of different samples. So a sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from a sample of size n. So we're just going to be looking at it for the mean, and then we'll do a little bit with standard deviation. So the sampling distribution of sample means, the X bars, is a distribution using the means computed from all possible random samples of a specific size n, taken from a population with mean mu and standard deviation sigma. So instead of looking at the X's, we're looking at a little small group, a sample from the population, and we're looking at the mean of those values in the sample. So it's a little bit theoretical here. We got a lot of this vocabulary and notation that we've been working with kind of repeated here. So we're going to look at the mean of the sample means. So we're used to just seeing the mean mu. Now this is not just the mean of all the data, but it's the mean of all the averages of all the little samples possible. So mu sub X bar is the mean of the sample means. And then we're going to compare it to our regular mean, the mean of all the values, mu. So mu is just the mean of all of our individual X values. Mu sub X bar is the mean or average of all the averages of all the different little samples you could take. So here's a little example that will hopefully make it a little bit more clear. A professor gave an 8-point quiz to a class of 4 students. Again, we're just using a small amount of data so that it's easier to look at. The scores were 2, 4, 2, 6, 4, and 8. Find the mean of all the scores of all 4 students, mu. So that's the regular average that we're used to. We add them all up and divide by 4. So we got 2 plus 6 plus 4 plus 8 divided by 4. This is going to be our regular mu that we're used to working with. So what's that? 20 over 4. So 5. So the mean, the average grade on this little quiz was 5 points out of 8. So if you wanted to figure out their percentage, you could do that, right? But this is the mean. Now we're going to look at calculating one of these mu sub X bar values. So determine all samples of size 2 without replacement. Okay, so we're not going to choose the same person twice. And find the mean of each sample. So let's just kind of go in order. So let's say we take these first 2 students, the 2 and the 6. Okay, what is the mean of that little sample? Well, the mean for a sample instead of the whole population is X bar, not mu, right? So 2 plus 6 is 8, and 8 divided by 2 is 4. So if we take the little small group, the little sample of the first 2 students out of the total of 4 students, the average for them is 4 points. Okay, so now let's take the student with the 2 and the student with a 4. What's their average? So 2 plus 4 is 6, divided by 2 is 3. Their average is 3. Now let's take the student who got a 2 with the student who got an 8. So 2 plus 8 is 10. 10 divided by 2 is 5. So for those 2 students, the average was 5 points. Oh, that was the same as the overall average. Okay, how many different little setups do we have here? Well, we have to do this. It's not replacement. We want 2 people out of 4 people. Oh, look. That's a 4C2. Okay. So this is how many little groups we will have. Okay, so we've got 4C2. We should have 6 of these little pairs. So with 4 students, you could make up 6 different pairs. And again, the order doesn't matter. You're just taking 2 students. So we got the student who got a 2 with everybody else. So how about the student who got a 6? Well, we got them with the 2 already. So now we're going to do the student with a 6 and the student with a 4. What's their average? 6 plus 4 is 10. 10 divided by 2 is 5. Now the student who got a 6 with the student who got an 8. 6 plus 8 is 14. 14 divided by 2 is 7. Their average was higher. Those were the two highest scoring students out of the 4 students. So we got everybody with the 6 points. The 4, we got 4 and 2, 4 and 6. So I guess we need 4 and 8. Those two students haven't been paired up yet. So 4 and 8, 4 plus 8 is 12. 12 divided by 2 is 6. So this was just for sample size 2. This was all the possibilities of matching up 2 of the 4 students. And so when you do that, each little sample has its own average or mean. Those are all these individual little x bars. So we've got 6 of those. So what this mu sub x bar is saying is that you take all these little x bars and you find the average of them. Okay? So find the mean of the sample means, mu sub x bar. So mu sub x bar is going to be the average of the x bars. So we take all these guys, 4 plus 3 plus 5 plus 5 plus 7 plus 6, and we divide by 6 because there are 6 of them. Okay. So all these x bars are getting averaged. And let's see what we get. 30 over 6, which is 5. Okay. So that's the same as that 5 we got up there, right? So we just averaged all 4 scores, and we got 5. And then here we took groups of 2, and we averaged all those averages, and we got 5. So the question is, why would you do all this work if it's the same, right? Well, before we did this work, we didn't know if it was the same. And so this is our one example that we're going to do to kind of show you that mu sub x bar is equal to mu. So what we learned is that mu sub x bar is equal to mu. Now, if we tried to do the same thing for standard deviation, which would obviously be a lot more complex because calculating standard deviation is more complex than calculating average or mean, we would find that the standard deviation of the sample means is not the same as the standard deviation. It's affected by how many pieces of data you have. So the standard deviation of the sample means is going to be the standard deviation of all the data divided by the square root of the sample size. So again, just so that you get more comfortable talking about these things, this is the mean of the sample means. That's the mu sub x bar. And this is the standard deviation of the sample means. Sigma sub x bar. Okay? So that's the symbols that are getting more complex looking since they have those subscripts, and this is what they're called or how you read them out loud. So a couple things to remember here. The sample means will differ from the population mean because the sample means were all those little x bars, right? So some of them were the same. These 2 x bars were the same as the mu, but some of them were different. It just depended on which group of 2 students we looked at. So the sample means do differ from the population mean, depending on the sample, and there will be sampling error. So the difference between the sample measure and the corresponding population measure due to the fact that the sample is not a perfect representation of the population. So when we had those little pairs of 2 students, sometimes we had the 2 highest scoring students, sometimes we had the 2 lowest scoring students, sometimes we had 2 students that were kind of in the middle. So it just depends on which sample you take, how closely that matches the true population. Here in this chart, we've got a little bit of information that's going to be a little bit different for when the population is normal or not normal. And also, it's going to go over some of the different kind of terminology, what these things are called. So if you have your sample means, your X bars, and you have a distribution, the whole population could be normal or not normal. We might not know. So if the population is normal, regardless of the sample you have, the shape of the distribution is normal, since the overall data is normal. If the population is not normal, then as the sample size n increases, so the bigger your sample is, the distribution of your sample becomes more normal, okay, approximately normal. Whether your population is normal or not, sometimes this mean of the sample mean is talked about in terms of it being the center, okay? And then the standard deviation of the sample mean, oh, I didn't write that up here. The standard deviation of the sample means, that is also called the spread. We know that that makes sense in terms of standard deviation telling us how spread out the data is. It's also called the standard error. Okay. So the shape might be a little different, but we're able to use these in both cases, the same formulas. So regardless of the shape of the underlying population, whether the whole population is normal or not normal, when you take all these little X bars for all your different samples, you find their sample means, then we know that these two things are going to be true. Okay, so it's got a mean of mu sub X bar, which is the same as mu. It's got a standard deviation of sigma sub X bar, which is sigma over square root of n, and that we're going to call the standard error. This is leading us to what is called the central limit theorem. Right at the top there, there's something you can look at in my stat lab if you're interested in a little visualization. The central limit theorem says that regardless of the shape of the underlying population, whether it's normal or not normal, the sample distribution of X bar becomes approximately normal as the sample size increases. So the bigger your sample is, the more that your distribution of the averages is going to look like a normal curve, even if your original data values aren't normal. So here's a couple of examples of how they might ask you to use these new formulas and just how we can make our way through all the wording and vocabulary. Suppose we're doing an experiment on weight loss, and we know that mu is 8 and sigma is 5. Okay, so that's for the whole population. We have all the data, and we know that overall the average is that they lost 8 pounds, and the standard deviation is 5 pounds. If we take a sample of 25 people, okay, so we don't know what the n is here, right? We don't know what the capital N is for the whole population, but we know that our little n is 25. How much weight do we expect our 25 people to lose, and with what standard deviation? So we can just make a list of what we do know. Mu is 8, sigma is 5, and n is 25. So one of these keywords is expect. Okay? So expected value is looking for the mean. Okay? And we just showed that the mean of our sample means is equal to the mean of the whole population. So we would still expect for this group of 25 that on average they would lose 8 pounds. So that's what we expect for this group of 25 based on what we know for the whole population of this study. What do we expect our standard deviation to be? Well, that is sigma sub X bar, and that is sigma over the square root of n. So for our overall population, we had a standard deviation of 5, but we're taking just a smaller group from that. We're just taking a sample of 25. So our sigma gets kind of scaled down. So square root of 25 is 5. So our standard deviation is just 1. So 1 pound. And so that's kind of some of the language in terms of expectation, okay? Expected value or expected standard deviation. This one down here uses a little bit different notation. Daily sales at a pizza restaurant vary from day to day, okay? Obvious. The sales figures fluctuate around a mean of $900 per day with a standard deviation sigma of $300. The mean sales for the 7 days in a week are computed each week, and the weekly means are plotted over time. These weekly means form a sampling distribution. What are the center and spread of the sampling distribution? So basically, the pizza place is not really caring that they might be busier or quieter over the weekday or weekend. They're just taking a whole week and putting that together. So their X bars are their weekly incomes, okay? Their weekly sales. So that's what they're looking at. So it's kind of hidden in here. We do know that the mean is 900 and the sigma is 300. But can you find the n? So the n is the sample size. So the n is the 7. They're taking 7 days worth together and combining that and finding the average for those 7 days. And that's where they're getting their little samples. So each sample has 7 days in it. So now the center is another name for mu sub x bar. You can see that from the table on page 2. So the mean of the sample means is going to be the same as the mean of the whole population. So we are going to expect that we could talk about it in this expectation language. We're going to expect that they have a sales of $900 a week. That is called the center. The spread, having to do with standard deviation, is sigma sub x bar. And that is sigma over the square root of n. So the original sigma, the sigma for the whole population, all this data that they tracked and calculated, they didn't tell us for how long they mapped this out, right? We don't know how many weeks they used to come up with this data, but they found that the overall standard deviation was 300, but now we're scaling that to deal with 7 days in a week. And we might need a calculator here, huh? We've got 300 divided by the square root of 7. So this is money, right? So I'm going to round to the nearest penny. So this is our spread, $113.39. Okay, so those are just some examples of what language you can see. So expect or center and spread that would indicate that now you need to use mu sub x bar and sigma sub x bar instead of regular mu and regular sigma. Now we're going to do one more thing with this new type of work, and we're going to look at our original z-score formula. And z-score has a mu and a sigma in it, right? Or we have looked at it in terms of a sample too, an x bar and an s. So if we have a mu and a sigma, well, now if we're looking at the sample means instead of just the regular data, we've got to plug in these formulas. So mu sub x bar is going to be the same as mu, but sigma sub x bar has this adjusted formula. So we have an adjusted z-score for sample means. Okay. So this is our new z-score formula right here. Original and new. Chapter 7, Chapter 8. So on page 4, we're going to look at a couple of examples and kind of figure out, well, how do we know if we're doing a Chapter 7 question or a Chapter 8 question? How do we know if we're just working with the original data or if we have these new sample means? Another thing we're going to have to be careful of is our notation. Excuse me. So our probability statements, if we're working with the sample means, then we're talking about x bar instead of x. So our probability statements will also have to have that x bar in there. And then we'll be asked to find the probability that the mean not just a data value. So that's one of the keywords that you're looking out for. So let's read this example and see if we think we have chapter 7 or chapter 8 going on here. It is reported that children between the ages of 2 and 5 watch an average of 25 hours of TV per week. Wow, that's too much. Assume the variable is normally distributed and the standard deviation is 3 hours. If 20 children between the ages of 2 and 5 are randomly selected, find the probability that the mean of the number of hours they watch TV will be greater than 26.3. Okay. What do we know? Okay, so the ages of 2 and 5, important, but not going to factor into our calculations. How about an average of 25 hours per week? That is a mean, but then here they're asking for a mean also. So it can get a little tricky. So this is our mean of 25. Okay, it's reported that that is what's true. We're assuming that's for the whole population. We do know that it's normally distributed, and we have a standard deviation of 3 hours. So that's our regular sigma, okay, for the whole population. Now we're looking at 20 children. So that is our sample size. That's our n equals 20. Find the probability that the mean of the number of hours they watch TV will be greater than 26.3 hours. So here's what's different. Here's what tells you that this is a chapter 8 problem. They don't say, if you pick one child, what's the probability that he or she watches more than 26.3 hours? They're saying, if you pick this whole group, what's the probability that the average for this group or sample is greater than this? So this is looking for the probability that the average that these 20 little kids watch TV is greater than 26.3 hours. Now, it's sort of like a chapter 7 question. We have the probability statement in terms of x, then we're going to turn our x's into z's and have a probability statement in terms of z, and then we're going to draw our picture and use our table to find our probability. But instead of x's, it's x bar. So to turn x bar into z, that's where we need that new adjusted z-score formula from the last page. So now it's x bar minus mu over sigma over square root of n. And just to give you some heads up, you got to be real careful in the calculator, okay? The calculator needs to know that the subtraction is in the top and the division is in the bottom. If you don't enter those parentheses, you're going to get it incorrect. So x bar, we're looking at the probability being greater than 26.3 minus mu of 25 divided by sigma 3 over square root of n 20. So in the top and the bottom, you do need both of those parentheses. They're going to be essential to get your correct answer. Okay, so we're going to round to 2 decimal places for z. That's what our table gives us, so 1.94. So now we need a probability statement in terms of z. So we turned our x bar into z. So an x bar of 26.3 corresponds to a z-score of 1.94. So what's the probability that z is greater than 1.94? Okay, so after I've got my probability statement with z, I'm going to make a picture. So 0 is in the middle. Z is a positive 1.94, so z is somewhere over here, 1.94. So I look at whether z is positive or negative first to figure out where the z is, and then I go back to my probability statement to see which part I'm shading. So z is greater than 1.94, so I'm shading in this right tail. So that's the area that I'm looking for. So if you remember from chapter 7, when it's a greater than or to the right of, I look up 1.94 in the table, but I do 1 minus this because the table is giving me all this area to the left, which is the white space, but I want this blue space. So 1.94 1.94 gives us an area of 0.9738. So our area or our probability for this answer will be 0.0262. Okay. So there's about a 3% chance that if you take 20 of these little kids, then their average is bigger than 26.3 hours. So this is working from the same 5-step process from section 7.2. I think it was page 9 in the notes. But we're working with X bar, a sample mean, a mean for a sample of 20 children. So we have the adjusted z-score formula. Okay, here's another one. The lengths of pregnancies are normally distributed with a mean of 268 days and a standard deviation of 15 days. Okay, they are not talking about a sample. We're assuming these are for the whole population. This is the data that we know. Now we have a part A and a part B. Find the probability that the length of a woman's pregnancy is less than 261 days. So your big key as to whether you're in chapter 7 or chapter 8 is what's your N? This is a woman. So this is like a little sample of one person. When we get down here to part B, a sample of 9 pregnant women, all with a specific condition, are randomly selected. Find the probability that the sample mean length of their pregnancies is less than 261 days. So here we have a sample of 9. So when we had just one individual person, one individual data point, that is what we did in chapter 7. So we are working with X here and X bar here. So same overall information, same mu and sigma, but the two different contexts here for parts A and B. So here we're working for this one woman. We're looking to find out what's the probability that her pregnancy was shorter, that it was less than 261 days. So I convert my X to Z. Z is X minus mu divided by sigma. So that's the old or the original z-score formula. And we did still need parentheses around the top there if we were entering this at one time in the calculator. So our z-score is negative 0.47, rounded to 2 decimal places. So our probability statement is, what's the probability that z is less than negative 0.47? I can make a picture. Here's 0. This time I have a negative z-score, so I'll draw it over here, negative 0.47. And I want the probability that z is less than this. So I'm shading over here. This is nice because this is a left or below question. So when I look up my value in the table, that is my answer. So looking up a z of negative 0.47. I got 0.3192 as my answer. Okay, so this is a chapter 7 question right here. Now this is a chapter 8 question. So we have a sample of 9 women. So now we have that adjusted z-score. Also look for this key. Here they say find the probability that her pregnancy is less than 261 days. Here they say find the probability that the sample mean or the average length of their pregnancies is less than 261. So this is important. This looks very similar, but it needs to be an X bar here, not an X. Okay. And now my z-score formula is different. So I've got now x bar minus mu divided by sigma over the square root of n. Sigma was 15, and now my n is 9, so square root of 9. If you're really paying attention here, you might actually notice that you could use this formula up here. What would happen is you divide this 15 by